You know when you look at a complex software system and just wonder, how does it all actually fit together? Well, the answer usually starts with a blueprint. Today, we're doing a deep dive into one of the most critical blueprints in all of software, the UML Class Diagram. We're going to skip the high-level fluff and get right into the technical details of how you create a design that's ready for code. So, where do we even begin? Well, every piece of software starts the same way. It goes from a simple idea to a concrete design. It's all about translating the what we want this to do into the how we're actually going to build it. And this slide, it just nails that transition. Look on the left. That's the simple analysis model for a bank account, just the basic idea. But then, look at the right. The design model is absolutely packed with detail. We're seeing privacy settings, specific data types, default values, and the exact signatures for every single operation. That evolution is what this is all about. To put it as simply as possible, analysis is the what. It's that conceptual model, the thing that describes the business problem we're trying to solve. Design, on the other hand, that's the how. It's the object model that lays out the precise technical plan for how we're going to write the code. Okay, let's move on and really break down the fundamental unit of our diagram, the design class itself. We're going to examine its internal structure piece by piece. What's so powerful here is the incredible level of precision. We don't just say balance, we specify it as dash balance double equals 0. Right away, that tells a developer it's private, it's a double, and it starts at 0. Same thing for the operations. Deposit isn't just a name, it has a full signature. Plus deposit, M double, void. That's public, it takes a double as a parameter, and it returns void. This precision even applies to constructors, the special methods that actually create the object. So let's do a quick recap of the syntax. For visibility, you're using a plus for public and a minus for private. Attributes follow that simple name, type, equal default value pattern. And operations, or methods, they get their full signature. And of course, we're also explicitly defining the constructors needed for creating our objects. Of course, classes don't exist in a vacuum, right? They connect, they interact. So next, let's look at one of the most common ways they connect, whole-part relationships, where some classes are literally built out of other classes. First up is aggregation. You can think of this as a has-a relationship, but it's a pretty weak one. The key thing you have to remember here is that the part's life cycle is not tied to the whole. It can exist all on its own. Here is the classic example. A computer has a printer. The UML notation for this is that open diamond on the whole side, the computer. And what's crucial here is that if you get rid of the computer, the printer still exists. It's totally independent. Now, contrast that with composition. This is a much, much stronger whole-part relationship. Here, the part is completely existence-dependent on the whole. If the whole object gets destroyed, its component parts are destroyed right along with it, no questions asked. The notation here is a filled-in diamond, and that extra visual weight is totally intentional. It signifies a strong, unbreakable bond. If A is the whole and B is the part, then B simply cannot exist without A. Think about a building and a room. If you demolish the building, the room is gone too. It's an integral, inseparable part of the whole. All right, so we've covered ownership. Now let's shift gears a bit and talk about relationships that define those is-A hierarchies and the formal contracts between our classes. This is an absolutely critical design distinction. With inheritance, you're making an is-A statement. A manager is a kind of employee. It gets both the public contract and the actual implementation. Interface realization, on the other hand, is a can-do relationship. It's a pure contract. A class that realizes an interface is just making a promise that it will provide an implementation for that contract's operations. And the notation reflects this difference perfectly. That solid line with a closed, unfilled arrowhead, that's your signal for inheritance. The dashed line with the same arrowhead, that signifies interface realization. They're visually distinct for a reason. They represent fundamentally different architectural choices that have huge implications for how coupled and flexible your system is. All right, it's time to add that final layer of detail to our associations. We need to make them so precise that a developer can implement them without any guesswork at all. So at the design level, every single association needs two key details. First is navigability, which you show with an arrowhead. It tells us which class holds the reference to the other. And second, you need multiplicity. This spells out the exact numbers, 1 for 1, 0 dot star for 0 or more, and so on. These are the main multiplicity patterns you're going to run into and implement over and over. You've got your one-to-one, many-to-one, one-to-many, and many-to-many. Each notation is a precise instruction for the developer about how to structure those relationships in the code. Now, a many-to-many relationship often needs some special handling. For instance, a person can have jobs at many companies, and a company employs many persons. So how do we model that? We resolve it by introducing an association class. Here, job becomes its own class, holding attributes like salary that really belong to the relationship itself, not just to the person or the company alone. Okay, we've got the syntax down, but knowing the syntax isn't enough. Now let's talk about the guiding principles that take a design from just being correct to being robust, maintainable, and genuinely high quality. First up, coupling. Think of this as a measure of how tangled up your classes are. If you make a change to class A and it forces you to go make a change in class B, they're coupled. And the fundamental goal of any good design is to achieve low coupling. And wow, this visual says it all, doesn't it? On the left, high coupling is a tangled mess. It's a house of cards. One change anywhere creates a ripple effect across the entire system. But on the right, low coupling gives us independent, self-contained components with clear, minimal interactions. That is the kind of resilient, maintainable system we want to build. The second core principle, sort of the flip side of the coin, is cohesion. While coupling looks at the dependencies between classes, cohesion looks inside a single class. It asks a simple question: how focused is this class? Do all of its parts work together to achieve one single, well-defined purpose? And our goal always is high cohesion. So what does high cohesion look like in practice? It means a class represents one single concept, and it does it really well. All its parts belong together. And inside that class, each method should solve just one single, focused task. That clarity is the absolute hallmark of a clean design. In the end, that's what a design class diagram is. It's the architectural blueprint for your software. So the question you have to ask yourself when you're creating one isn't just, is the syntax correct, but does my blueprint build a rigid, brittle structure that's going to crack under pressure? Or does it lay the foundation for an adaptable and resilient system?